particular map P on the operator system, but this element V star, if you look at the element V star, that's an element in the C star algebra generated by V, and Pn of V star minus PV star is nothing but V star minus identity. That is actually non-zero. So you don't have convergence on the C star algebra, whereas you have convergence on the operator system. So this means that this map P is not a non-commutative DKW operator for that particular operator system. Yeah, for any sequence Pn, if you take arbitrary sequence Pn, Pn converges P on the operator system, it should converge to this. Yeah. Okay, so as I said earlier, define non-commutative DKW operators by replacing the non-convergence with weak convergence. So here we will take weak operator topology. So we say P is a non-commutative DKW operator for P if Pn converges to P or Pns converges to Ps in the weak operator topology of B of H for every S, then it should converge this Pn of A converges to P of A for every A in the C star algebra generated by that S. So this is more interesting because this convergence is nothing but the convergence of, usually we talk about the convergence of CP maps in BW topology. So this means that if Pn converges to P on S in the BW topology, it should imply that Pn converges to P on the C star algebra A in the BW topology. And here we observed an interesting result. So this says that we start with an separable operator system, and you look at A to be the C star algebra generated by that operator system. And you take a CP map phi from A to B of H, where H is a separable Hilbert space. The following two conditions are the same. An operator P, that UCP map P, is a non-commutative DKW operator for S with respect to this weak operator topology or in the BW topology, if and only if P restricted to S as unique CP extension. That means that you have, so there is this theorem in operator algebra which says that if you have a CP map on the operator system, you can extend to a CP map on the C star algebra. And what we observed is that extension is unique. So some map P is a non-commutative DKW operator if and only if the Arvisan extension of the CP map P restricted to X is unique. Right. So again, the proof we use proof is not that much hard, but we essentially use this compactness of UCP maps from A to B of H. So this is compact in the BW topology when this H and A are separate. Okay. So this is one example where, so again this theorem also helps you to construct examples. So rather than looking at the convergence of arbitrary CP map, it is enough to prove the unique extension. Right. So here also for this example, if you look at this map, P from M2C to M2C and P of ABCD goes to its diagonal, A0, 0, then this, you can show that this map is say non-commutative DKW operator for this operator system generated by identity E11 at T. And here is an infinite dimensional example where we will take the operator system to be the trace class operators with operator system generated by the trace class operators. Sorry? Right. Yeah, this is not multiplicative, right? Yeah, but this doesn't preserve multiplicative. This P is not multiplicative, right? Yeah. Right. Yeah, come to that. As mentioned in the talk. We'll come to that. But this map is not multiplicative. This is a proper non-trivial example. Okay. So this is an infinite dimensional example in the case of trace class operators and compact operators. So here also this map is not multiplication. Right. Again, we are taking conjugation by this right shift operator. Yeah, sure. Thank you. Yeah, here is a simple map which has two extensions. You look at the operator system or the subspace set of all matrices of the form A, B, C, A, and you consider the previous map on this operator system. This has two extensions. Basically, you can change the diagonals. A0 will be. Yeah. Also, we observed that this one can define this. One can replace this convergence in norm by SOT, and you can prove that the convergence with respect to, in this case, the convergence with respect to SOT and this WT are the same. Essentially, using that main theorem. So while searching for this, while searching for identifying these non-commutative DKW operators, we end up with uniqueness in RV selection theorem. So this was not studied in literature much, except for the case of representations, as he said. So even though for a special class of representations known as boundary representation, it is studied and studied by RV. So boundary representations are basically irreducible representations of the C-star algebra which has unique extension from an operator, given operator. So, and these boundary representations are the non-commutative analogs of what are called Choquet boundary in the classical theory and classical function theory, and this Choquet boundary is connected to Coroquian sets, and here in the non-commutative setup, a stronger version of Coroquian sets are called hyperligid sets, and Arvidsson proved some results related to the connection between our boundary representations and hyperligid sets. So we generalize this hyperligid set and the following way. So you have a C-star algebra A and a set of generators of A, call it as S, and you have a CP map eta from B of H to B of H, and we say S is hyperligid with respect to eta for any sequence of CP maps psi n from B of H to B of H, and for any faithful representation sigma from A to B of H. If psi n composition sigma converges to eta composition sigma on the operator system, it should imply the convergence everywhere on the C-star algebra. So one can easily observe that a connection between non-commutative DKW operators in this context, say some set S is, or an operator system S is hyperligid with respect to eta, if and only if eta composition sigma is a non-commutative DKW operator for a free faithful representation sigma. And along the lines of Arvidsson, we characterize this hyperligidity with respect to commutative DKW operator for the operator system S in norm, and condition 3 says that pi composition eta restricted S has unique CP extension. That means pi composition eta is a non-commutative DKW operator in terms of WT. So, and we have one more condition in terms of star form. So this is an ongoing program, and you have, of course, you can ask a lot of questions. First of all, the main theorem is proved only for the separable Hilbert space, and you can try for arbitrary general Hilbert space. And this uniqueness aspect in the service mechanism there is unexplored in the literature except for representation. For general CPMF it is not studied. So yeah, one can study that, and you can make further connections between non-commutative BKW operators and this hyperunity with respect to UCPMF. And of course this fourth and fifth problems that arises naturally given an operator system. What are the non-commutative BKW operators for that particular operator system? Or you can ask the reverse question. Given a CPMF, what are all the operator system for which this P is a non-commutative BKW operator? So yeah. So, thank you.
Questions? Okay, so
right. Right, that means here you have to take convergence with respect to WOC. Right. Every CPMF? No, how that's possible? Right. Correct. Right. Yeah, that the third condition will be equivalent because the definition that with convergence with respect to WT. Yeah.
Here it is not represented.
Yeah, correct. Yeah, this is actually a generalization. That itself as a generalization of MLS solution. Yeah, right. Correct. Here we are, rather than representations, we are taking general CPMs. That is the difference. That's the generalization here. Yeah, okay, we'll discuss it. Yeah, I'm not asking.
Yeah, you can discuss it. So, I think next talk is at 2:30, so maybe we can just thank the speaker once again. We shall resume at 2:25.
Thank you, sir. I would like to invite the chair to give a token of appreciation to our speaker. Kindly note, next session is about to resume. I kindly request everyone to come and take their seats. Our next talk is about to resume.
প্রথম দিকে
So let's start our speaker is Professor Elthuruth, and I invite the chair to introduce our speaker.
Okay, so now speaker is Elthuruth from PUSAP, third speaker, third and final. He is PhD in Germany and he is post of ICOST.
Thank you. So, thank you very much to the organizers for giving me this opportunity to speak in this conference, especially Professor Narayanan, who has been at the head of the address. So today I am going to talk about the sister extreme points of positive operator value measures. So, positive operator value measures is very in popularity now because mainly because of physics quantum measurements, these are nothing but positive operator value measures. So you may have come across this object. Our motivation to study positive operator value measures came from completely positive maps. So this is what is the notion of sister extreme points of positive operator value measures. So I mean convexity generally, as many of you have seen by now, you have a convex set. So any 2 points, you take the straight line joining them, it will be inside the set. That is the usual convexity notion. Coefficients that gives you the convexity condition is coming from Q. C or R, wherever you are working with. We actually are interested in C-star extreme points or C-star convex combinations. That is, these coefficients will now be some operators. Okay, so that is the main thing. And talking about extremity in that sense, like when you have convex combinations with respect to coefficients coming from operators, what about the extreme points in that set of? Like now, positive operator value measures is the main talk. So this is basically a joint work with Professor Rajrama Bhatt and Dr. Manish Kumar. So this work mainly what we addressed was like the notion of C-star extreme points of completely positive maps was started by Parnik and Morens in the paper on C-star extreme points of generalized states of C-star algebras. And there they could only say that you have finitely many points and your set of UCB maps is taking values in the finite dimensional Hilbert space. Then the sister extreme points will be also extreme points in the sense of this coefficient sign from the field, and there will be only star homomorphism. They bring in conclusion about what happens to when the Hilbert space is infinite dimension. So our main purpose of this work was to address that question, for which we went via this notion of positive operator value measures. So let's start with the talk. So we'll first give an outline, we'll first discuss what are the unital completely positive maps briefly. Then we'll briefly talk about the order relation among unital completely positive maps, and then C star points in that set. And next we will come from completely positive maps to positive operator measures. Those are these POVMs. This is the short form for positive operator measures. And there is a connection, interrelation between one-to-one, like not one-to-one, but there is a connection between completely positive maps and POVM. We'll exploit that, we'll see that, and then finally we will restrict to the special case of POVMs with commutative radius. We will see what is commutative radius means, and then what are the C points in that setting. Okay? So yeah, so this is just part of the whole work that we are going to present, like the paper that Sir and Manish. Okay, so start with what are unital completely positive maps. So you take a unital C star algebra a linear map A to B of H. Here H is typically a defined separable Hilbert space. Is said to be positive. All positive elements in A, those are of this form, A star A. You have phi of A star A is also a positive operator in B of H. So this notion of positivity can be extended to C star algebras M and A. These are like n cross n matrices with the entries are coming from the C star algebra A. So you say a linear map phi, so this M and A can be seen as the tensor product of M and C with A. So you take this map phi, A to B of A, you extend it to this level of matrices, M and A to M and B of A. And when you say that this map is a positive linear map, n positive, if it is this map is a positive linear map. So in the case of n is equal to 2, it will look something like this. So the entries are all from the C star algebra A, and these are the all operators in B of A. And if this map is positive, then we call phi is 2 positive. Finally, a linear map is said to be completely positive if this holds for all n in the natural numbers. A typical example would be a star homomorphism. Typically, it naturally satisfies this condition of A star A goes to something T star T. T will be exactly phi of A itself. Phi of like the extension of A to the M. Okay, so now the most important like the notion of this C star algebra, the completely positive maps is this time spring dilation theorem. So you have already seen some dilation of operators, right? I mean, you have an operator defined on some Hilbert space, and then if you enlarge the Hilbert space, this nice operator like contractions, they become isometries or unitary. So it was very much in that line that Steinspring had this. Now you have an algebra of operators. So what you do is, for every completely positive map, you have this Hilbert space, a bigger Hilbert space K, and a unital star homomorphism, where and this boundary operator V from H to K, so that this H is sitting inside K, such that phi A is equal to V star phi A V. That is, V is, so in particular if phi is unital, this will imply that V star V is equal to identity. So that means that V is an isometry, right? And so it's like taking H and keeping a copy of H sitting inside the bigger Hilbert space K. That is the V of H. And every completely positive map is like a cut down of a star homomorphism on the bigger Hilbert space to this smaller subspace V of H, which is sitting inside K. Okay, now what about the uniqueness of such representations of a completely positive map in terms of the homomorphism? So here comes the notion of a minimal dilation. So you say it's a minimal dilation if the this square bracket is basically the closed linear span of this set phi of A, which the whole algebra, C star algebra A, B of A, this closed linear span. You name this is K. If that K that you got, the bigger Hilbert space that you got, is same as the closed linear span of this phi A B of H, then we call that the representation, Steinspring representation is minimal. And you have a certain kind of uniqueness here, like given a C star algebra A and a completely positive map phi from A to B of H, if there are two such minimal dilations, Steinspring dilations of this completely positive map, then you can get a unitary U from one Hilbert space to K2, such that that unitary intertwines the two representations. Basically, it takes the isometry V1 to the isometry V2 and this representation phi 1 to the representation phi 2 by a conjugation. Okay? So now we come to the notion of C star extreme points of unital completely positive maps. So for a C star algebra A, denote the set of all unital completely positive maps by this UCP A comma H. A C star convex combination of maps phi 1 and phi 2 is given as something like this: T1 star phi 1 T1 plus T2 star phi 2 T2. Just previously you had just lambda 1 lambda 2. Now here you have conjugation by operators T1 and T2. T1 and T2 are any operators in B of H. So I have just named it some phi 1, 2. This is a sister convex combination of these UCP maps, phi 1 and phi 2. And the main point of convexity is this, that T1 star T1 plus T2 star T2 is the identity operator in the Hilbert space, which is like the 1 in the case of the field. Okay, and now the very interesting thing is that ordered relation among in the set of completely positive maps. This was mainly started by Arveson, and he gave this notion of being dominated by another completely positive map. So phi 1 is said to be less than or equal to phi 2 if phi 2 minus phi 1 is again a UCP map. So this is a partial order in the set of all unital completely positive map, and this characterization goes to Arveson. Like if you have the Stein-Spring representation of phi I as given by this the isometry Vi and the representation phi I for I is equal to 1, 2, and such that they are minimal representations, that is Ki, the Hilbert space in which this phi I is acting as algebra of operators, is the closed linear span of this pi I A Vi H. Then what it says is that there exists a contraction T belonging to B K2 comma K1 such that T V2 is equal to V1 and T pi 2A is equal to pi 1 A T. Okay? Yes. Oh, okay, yeah. Yeah, it's in C. Yeah, thank you. So, yeah, so this is the thing. And Arveson also used it to give notion of extreme point UCP maps. So I have not written it. So if you take a Stein-Spring representation of a UCP map and take an operator and you take the set of all commutators of pi of x, like you have the representation V pi and space K for the UCP map phi, and you take the commutant pi of A commutant. So and for every operator which commutes with pi of A, you can go to the projection, like you can project it down to the smaller Hilbert space given by V of H. Like V is an isometry, it's making H sit inside this bigger Hilbert space K. So T restricted to V of H, T is the operator in the commutant of pi of X, and then again projection back. So that map T goes to from the commutant of pi to the V of H is injective. Then you have that the CP map is going to be an extreme point. That means coefficients are coming only from the scalar field, not from operator. Okay, so now first note that this phi 1, 2 that I have written in the last C-sub combination, that is completely positive. This can be easily seen from this kind of characterization of CP maps. I'm not going to read. And also it will be unital, because if you take phi 1, 2 of IA, it will be T1 star phi 1 of IA is a unit in A. This will be phi 1 of 1A is 1, so it will become T1 star T1 plus T2 star T2. And already you have this convexity condition, that will be identity. So therefore phi 1, 2 belongs to this unital completely positive maps on from A to H. Okay, now what is the notion of sister extreme point? So element phi in this set of UCP A comma H is called sister extreme. If whenever you have such a sister convex combination representing the map phi, this is phi i's are belonging to UCP A comma H with T i's invertible. Now here when you are talking about sister convex combination, you need not have T i's are invertible, but when you are talking about extreme points, sister extreme points, T i's are invertible, and in that case, we so such that this Ti star Ti is identity, we get phi is said to be a sister extreme point if these phi i's whose sister convex combination is phi is unitary equivalent to phi for each I. Okay? So that is there exists ui's in the boundary operators on the Hilbert space such that phi is unitary equivalent to each of the phi i's. This is what. Now what are examples of such extreme points? So if you go to the Hilbert space is one dimensional, that is C, then the notion of C-star convexity is same as the notion of the scalar convexity, like lambda 1 plus lambda 2 is equal to 1. So star homomorphisms are already, you know that on a commutative C-star algebra C of X, all star homomorphisms are extreme points in the set of states. Like they are all the states. So therefore, they will be satisfying the C-star extreme condition. Then on a general C-star algebra, the pure states on C-star algebras, they will also satisfy this condition. So pure is basically if you have like psi is less than or equal to phi, then psi should be of the form lambda times phi. Those things. And then inflation of pure states is also there. Like if you take the dimension is some finite dimension reverse space H is here, then D of H will be MNC, and this map, that's the inflation, like you take a pure state phi, like here in example 2, and then every element A, it will map to a scalar C, but then you inflate it to a n cross n matrix by taking the identity matrix. So these kind of maps are also going to be C** points in the set of all unitary completely positive maps. And finally the star homomorphisms. They are always C** points of UCB maps, but not all star homomorphisms are C** points. There are examples of C** points which are not a star homomorphism. This is, you take this to a Clese extension. So if you have phi, so this C of T is the continuous functions on the circle S1, and B of H, bounded operators on the Hilbert space, where H is exactly this Hardy Hilbert space, H2, T, the circle, comma M. So you take basically L2 of the circle. So each function in L2 you have the Fourier series. The Hardy Hilbert space is the analytic function in that set. So it's all the Fourier series whose only positive coefficients are non-zero. So and the map is, you have maybe seen before. This is like you project to from L2 of, so I have written it down. PH is the projection from L2 to H2, because H2 is sitting inside L2, and MF is the multiplication operator corresponding to this representation. You take a function F C of T and you multiply G to F of G. Okay, that is the representation that I was talking in this Steinspring representation. So this phi will clearly give you CP map, because it is like of the form E star some representation by V, where is this projection basically. V star is the projection. Okay. So yeah, so that has to be written clearly. Like V will be the inclusion of H2 inside L2, and this projection is basically going to be V star V. Yeah. No, V star. Oh, sorry. Projection, yes. From H2 to H2. Okay. So let's not go into that. And then phi is given as a proper C-star from this combination of phi I. So you take this phi, and suppose you want to now prove that this phi is a C-star extreme point. So you take a proper C-star convex combination of this phi as phi i's. So you have written something like that. Now look at this particular function z on the circle. So it is e to the power I theta. Now note one thing, that z bar is the constant function 1. Okay. So then, and also note that phi z is the right shift operator on the Hardy Hilbert space. Why? Because this is like when you multiply by z, you are taking a polynomial and you multiplying by z means you are just shifting the degree of the polynomial by 1. So a0 will go to the first place and so on like that. So it's the right shift operator on the Hardy Hilbert space, and it is all of know that is an isometry. The adjoint is the left, and then you have isometries are C** points of the closed unit ball of operator. This is a result by et al. So they have proved this, and using that you can say that this phi z has to be a C** point. So if you write phi z as a C* convex combination of the phi I z's, phi I z has to be ui star phi z ui for some unitary ui. So from there also you get phi I. So phi z is an isometry and it is unitarily equivalent to phi I. We'll tell you that phi I is also an isometry, phi I of z. So phi I of z is an isometry, we will get this relation. Phi I z is equal to 1 is equal to phi 2, which is again same as I of z star z. Okay. So this paper by Bruns and Salinas, they show that if you have that previous relation, this last relation that I written down, then you have this condition, this pi I of z vi is equal to vi by phi I z, where phi I has this as its mean representation. So vi is the isometry, v pi I is the representation, and the Hilbert space on which it is represented, that is minimal, that is the closed linear span of that. Okay, so from that relation, pi I z vi is equal to vi phi I z, you can write for any analytic trigonometric polynomial q. So basically it's a polynomial z, so that will also be giving it this relation. I mean, you can just use this kind of commutativity in some sense. Okay, and you will get it for every polynomials. So analytic polynomials, and in particular, you will have that this condition holds for all q's. So therefore, this condition will also hold for all q's. That is also, you can write it down. Phi I q will be equal to ui star phi I q, phi q ui, from the fact that phi I z is ui star phi z ui. So this gives that all the analytic trigonometric polynomials q, you have phi I of q, where phi I is one of the CP maps in the sister converse combination that you have written down for phi. That is a unitary conjugation for phi q. Okay. So this, now you use the fact that the system P plus Q star, where P and Q are analytic trigonometric polynomials, is uniformly dense in C of S1. Okay, so this is uniformly dense. This is like, and then you can use, this is like Weierstrass approximation theorem, and you have that for every continuous function f in C of the circle, phi I f is some conjugation of phi f by some unitary ui star phi f ui. So therefore, for every f we have shown that phi if is unitary conjugation for phi f, so therefore phi is a sister extreme point. And typically this example is a one where the map is not a homomorphism, because you will have functions which are not analytic in C of S1, so when you multiply by them, fg, and multiply first f and then you will get different. Yes. Yeah, pure UCP maps will be pure. Yeah. It will not be irreducible representations. It's like if you are talking about inflations. Yeah. Pure UCP map won't be different. No. But inflation, your stress will be. Yeah. Okay, now we come to the topic of what is a POVM. How much time? Okay. So we have seen the spectral bounded normal operator, right? I mean, you have a bounded normal operator. Then on the spectrum of the operator, you have spectral measure. That is for every Borel's sum. You can define projections, right? I mean, so this is kind of a generalization of that concept. You have X a measurable space with a sigma algebra of X and H be a Hilbert space, typically infinite dimensional. A positive operator value measure POVM on X with values in B of H is a map mu from OX to B of H, such that mu A is positive in B of H for all A, and for every H comma K in H, the map mu H comma K, this is the, you take the inner product H comma mu A K, this is going to give you a complex measure on X. Okay? So this is the definition of a POVM, and it's just, if you have the measurable space is a topological space X, the POVM is called regular if this complex measures are regular. That is the notion of approximation from inside by compact sets and outside by open sets that will hold. And it's normalized if your mu of X is identity operator. And if it is a projection value measure, PVM, if mu A is a position operator for each A. Okay? So these are the spectral measure that I spoke about, the normal operator measure that you get from a typical bounded normal operator. That is all PVM, that is every operator, every Borel set A goes to some, every set A in the sigma algebra of X goes to some projection operator, and also it is normalized, that the whole set is identity. Okay, now this correspondence between completely positive maps and POVM. So start with a unitary completely positive map. So POVMs in the setting of completely positive maps only coming first, commutative sister algebras. Only then you have a space X on which you want to get a measure which is operator value measure. Now we start with a commutative unitary sister algebra. Now given a unitary completely positive map phi from C of X to P of H, for fixed H and K, you define a bounded linear functional on C of X. This is this map. And this is a positive linear functional if H is equal to K. For fixed H comma K, you get a Borel measure, regular Borel measure mu HK on X by the Ries-Markov representation theorem. And such that you can write down that inner product H comma phi fk as the integral of f over this measure mu H comma K. So for every HK, you get a measure mu HK, which is also regular Borel measure. And typically this is positive because this functional becomes positive when you take H is equal to K. So this measure will also be a positive value measure. Now, then for each bounded measurable function G, you get this, you can extend it from fc of X to every Borel measurable functions G, and you get this sesquilinear form on H cross H, which is bounded by this norm. And so by Ries representation theorem, you obtain a unique bounded operator phi tilde G belonging to the operator B of H, which will give you that sesquilinear form. This is this representation. So you define your mu phi of A. So you have the characteristic functions of your sets A in O of X. They are all Fourier measurable functions in this sigma algebra. And so mu phi of A will be the phi tilde of the characteristic function. That is how you define a positive operator value measure. So it is a positive value, it is a regular POVM, mu phi from OX to P of X, so that mu phi and the whole space X will have to be the identity. Because when you take the identity map, like you take the constant function 1, phi of 1 is going to the identity operator, so mu phi of X will also go to the identity operator. And the converse process also holds. You start with a POVM, you can go back through this process and arrive at a completely positive map from the continuous functions on X to A. So we restrict to regular measures to get uniqueness in between UCV maps and POVMs. Like if you start with a completely positive map phi, you go to its measure mu phi, and then it take back its completely positive map phi. That should be the original completely positive map phi. And also mu, if you start with a POVM mu, you take the completely positive map corresponding to mu, then you take back mu again for that completely positive map. You should get back the original mu. For this, when you come from a completely positive map to a measure, you are getting regularity for free because you already have continuity of that linear function around phi of C of X. So and phi of 1 is also mu phi of X. Okay, all that we have shown before also. And also similar to Stein-Split representations of completely positive maps, there is a minimal non-marketization for POVMs. So it will be some pi which is a spectral value, that is a projection value measure such that pi of X is identity. So this form is same as that of completely positive maps, right? I mean, this POVMs and completely positive maps kind of are same, like they're just two different faces on the same coin when you take the algebra to be the C of X. Okay, so you have a pi is a projection value measure, so all these sets will go to some projections. V is an isometry from H to H pi, and H pi is the whole space, bigger space you are representing your POVM as a projection value measure. Okay, now definition of C star extreme points among POVMs. So you start with the topological space X, restrict to the setup. Now I'll restrict to regular normalized POVMs. As you said, that then there only you have a one-to-one correspondence denoted as RPHX. And then again, like before, we defined C star converse combination for this mu. It's called a C star converse combination. And when the TIs are invertible, you say that this is a proper C star converse combination for mu. And you observe that the set RPHX is closed under such C star converse combinations. So if you take C star elements mu I in RPHX and you take this sums Ti star mu I Ti, that will again be a positive operator value measure. And also since the summation Ti star is identity, therefore when you evaluate it on the whole space X, you will get mu of X is equal to identity. So this C star converse combinations, it is closed under C star converse combination. And also we have that the regular like the regular POVMs on X, these are the subset of all possible POVMs on X. That is PHX represents all positive operator value measures on X on the Hilbert space H. So a normalized POVM is called a C star extreme point in PHX if whenever this a proper C star converse combination for mu, then each mu I is unitarily equivalent to mu. Just like before, that is there exist unitaries like this which intertwines. And now C star extreme points in RPHX. So you define similarly in RPHX. So like the last was in PHX. This is the set of all positive operator value measures normalized, and this is your RPHX, the subset of regular positive operator value measures. Here the first observation is that if mu is a regular POVM, then when you conjugate by some operator, that will also be a regular POVM. This is just approximation property, so it will hold. And then this is another, like if you have mu is dominated by this mu, that means for every set A in your sigma algebra of X, mu of A is less than equal to mu of A in the sense of A minus mu A minus mu A is a positive operator, then mu will also be regular. This is also another observation. Again, because of approximation property, they will not take care of this algebraic thing. And so, if mu is a regular normalized POVM, then mu is, so if you now restrict to regular normalized POVM, if mu is C star extreme, when you write a C star converse combination of a POVM, you have that each T1 star mu1 T1 will be dominated by this mu. So they will be again regular POVMs. The set of C star extreme points in the set of PHX is the same as C star extreme points in RPHX. Okay, now so let's come to the characterization of C star extreme points in PHX. This is basically the same kind of work was done by Zoe and Faranek in the paper, like this the structure of C-star extreme points of unital completely positive maps, and we take it to the set of PHX, that is all POVMs, normalized POVMs, mu from OX to B of H, and we characterize C-star extreme points in that setting in PHX. So this is if and only for any positive operator D belong to pi OX commutant with V star dV being invertible. These all things are same, except that Zoe said that there was a unitary U belonging to pi OX commutant such that U star U d to the power half is, no, this condition was not there because U is a unitary means U star U has to be identity, and such that there exists S such that you will have U d to the power half V is V of S. Now we observed that you don't get a unitary but you get a co-isometry. So I will say what is the proof. So you assume you start with mu is C star extreme. Now you take this D from the commutant of pi of OX, like with V star dV being invertible. So using this D, so you can scale it down by some alpha such that norm of alpha D is a contraction, it's less than equal to 1. So then 1 minus alpha D will be invertible, and using 1 minus alpha or 1 minus alpha V star dV and V star dV, you can break down your this mu C star extreme point as a combination of two POVMs, 1 and mu. And we get a minimal different, so using D we get this C star convex combination using D, and we get a different minimal normal dilation for U. Using the extremity of mu, this terms that are appearing in the C star convex combination, each will be dominated by mu. So the first term will be less than or equal to mu, so it will be unitary. From that you will get a unitary W1, and from the other also you will get that, and using this you get a different normal dilation for mu, the original mu that is started with, that is pi V1K. And this V is the isometry in BH comma pi, H pi. That is the map which is taking the Hilbert space to the Hilbert space H pi. And what we did was this V1 actually will, so once we get this, is an isometry in the minimal normal dilation for mu. So then this K to the Hilbert space H pi, they will be a unitary that will intertwine them K to H pi, right? But because this is a minimal normal dilation for mu, and this is another minimal normal dilation for mu, so there will be a unitary between H pi and K. Okay, so the U from, that is the U from K to H pi, but K is sitting inside H pi. So what we extend this U to the whole space H pi by taking 0 on the ortho complement. So that's why we don't get a unitary, we get a U star projection onto the range space of this d to the power half, basically. That is why you will get this condition, U star U d to the power half is equal to d to the power half. 5 minutes, okay. So then the converse is also something similar. You have any positive D, IH star D, IH invertible, that means D itself is invertible because IH is the identity, and you take S to be the d to the power half and U also the identity map. So then it satisfies the condition U d to the power half B is equal to Bs, and U star U d to the power half is equal to d to the power half. Just trivially, because U star U will become identity, this will be d to the power half is equal to d to the power half. Here also you will have basically d to the power half, and V is also identity, so it's the same. Okay, so this now tells you that if you have every spectral measure will be a C star extreme point in PH of X. Okay, so now we restrict to POVs with commutative range. Now you take mu is commutative POV if this holds, right? Mu a dash is equal to mu a dash, mu a for all a dash. The special case is this, mu a intersection a dash is mu a dash. If this condition holds, then you know mu a and mu a dash will come in because both will give you this same operator. So this is a special, very easy theorem. You have equivalence between this condition mu a intersection mu a dash as same as mu a will be of projections. So this is just algebra, there is nothing more to it. And but note that this need not mean that every commutative POV is spectral, because a commutative POV is a more general condition. Mu a dash is over mu a dash mu a. It is not necessary that it will satisfy this condition. Okay, But if it satisfies this condition, you know that they are projections. Okay, so this is the theorem that was already known to physicists, that a commutative normalized POVM, that means the range is commutative of this POVM. It's an extreme point, that is in the scalar value sense, if and only if it is spectral. But it was not known about anything about C star extreme points. Now what we use is, we use this notion, mu A intersection A dash, into the next thing, that we have this theorem, that is, if mu be a C star extreme point in PHX, we are not starting with mu as a commutative C star extreme point, just any C star extreme point, and if E belongs to OX is such that mu A mu E is equal to mu E mu A for all A subsets of E. This is typically what holds for atomic measures. I mean, you have for every subset A of E, either mu A will be 0 or mu A will be E, in which case it will commute. So in that case, basically this applies very nicely. So we have this theorem. Here basically we used another characterization of Zo of C star extreme points, and also the fact that we got a Borel functional calculus, that we have a very specific application of Borel functional calculus to get this, that if this condition is satisfied, then mu E is a projection. In particular, you have, if the range is whole commutative, then it will be a projection always, because this will be trivially satisfied by every E. So this is the result in the paper. So mu OX from B of H be a commutative normalized POVM. Then mu is C star extreme in PHX if and only if it is a spectral measure. Okay? So this is commutative. Note that the Toeplitz extension was not commutative POVM, because that was not multiplicative. So that is, but that was C star extreme. This is only about commutative POVMs, which are C star extreme, will be all spectral measures. Okay, now this last theorem will exploit to conclude about atomic POVMs. As I said, this is the notion of atomic POVMs. So if A is B subset of A is called an atom if either mu B is equal to 0 or A intersection B is an atom. Or is this is the definition. Mu B is equal to 0 or mu B is equal to mu A. Then this is also true. And if mu be a C star extreme point in PHX, then mu E is a projection for every atom E for U, because it will satisfy the condition of this theorem. Just directly it will follow mu E is a projection. In particular, for every X in your set X, mu X is a projection. Therefore, if you take a countable set A, you have this collection mu X mu I, mutually tonal projections, that you can show very trivially because one will be dominated. And therefore, the last theorem, you have this, an atomic normalized POVM, mu, this is only the atomic normalized POVM, we want to measure the space X, is C star extreme point in PHX if and only if it is spectral. In particular, if X is a countable measure of space, then any C star extreme point of PHX is spectral. This helped us to conclude about also completely positive maps on C of X. So these are the references that I use, and thank you for it.
Question.
Yes, I mean, so you have two POVMs, so on the same measure space, now every POVM can be decomposed as a direct sum of an atomic part and a non-atomic part. So the atomic part, you know that like now you're talking about comparing two different POVMs. Absolute continuity. So, okay. Yes. Random recordability, okay. Yeah, here also we'll have such a random recordability. If you are like dominated by, if mu1 is dominated by mu2, that will be corresponding to Arvisa's work basically. Like it will give you that one is 0, will give the other is, yeah, domination implies, yeah. So, no, I have to think about it now.
Okay, thanks, Tadavata.
Thanks.
Thank you, sir. I would like to invite the chair to give a token of appreciation.
Now.
Everyone should be back by 3:20 p.m.
arises. There have been several examples or counter-examples about self-adjointness in the literature, which I want to recall, some basic examples, and then I want to explain the main result, which gives a characterization of self-adjointness of tuplets operators, which is it gives a sufficient criteria to prove self-adjointness of tuplets operators with unbounded symbols, of course. And in the last part, I want to explain some conjectures which are related to this, and also examples and extensions of the result to operators with operator-valued symbols again. So this is my aim. I want to characterize self-adjointness for a certain class of operators, which are called tuplets operators. These are operators which come with a symbol, and these symbols are generally unbounded, and they could be also operator-valued. And these operator-valued symbols somehow are induced by the applications from physics. So let me just recall a very basic theory. So here we work on a complex Hilbert space, H, and we have an operator, T, which is densely defined and unbounded. D of T means the domain of this, and then as usually we can look at the adjoint operator, which is denoted by T star, and that has again a domain which is denoted by dt star, and this domain consists of all Hilbert space element Y, such that there is some set in H, such that inner product Txy with x equals inner product x of z for all x in the domain of dt of t. And that, of course, means that the functional which assigns to x the inner product Txy or some y extends to a bounded functional on the Hilbert space, and this extension must be unique due to the the assumption that the operator is densely defined. So this is the standard definition. And then the question is, how can we actually, so what we want to do is to look at the problem of self-adjointness, which means that T equals T star, and one can ask how can we prove or disprove self-adjointness? And here's the standard result from the von Neumann theory, which tells you that whenever you have a symmetric operator, then self-adjointness, which means T equal T star, has these three equivalent formulations. So T is self-adjoint, T equal T star is equivalent to T being closed, and the kernel of T star plus minus I identity is 0, which is equivalent to saying that the range of T plus minus I identity is the whole Hilbert space. So these are very useful characterization which we can use to prove essentially or self-adjointness. So why is this important? Of course, self-adjoint operators have a long history, and you can say that this notion of self-adjointness for unbounded operators is the correct generalization of self-adjointness of bounded operators, because it produces a real spectrum. So this is the correct one over narrowly saying closed symmetric operators. And then, of course, these operators are essential in the mathematical foundation of quantum mechanics, as was introduced by von Neumann a long time ago. And so they appear in quantum probabilistic interpretations of quantum mechanics. They are used if you want to produce partitions of unity into projections. Quantum observables are thought of as self-adjoint operators, and of course these days also the study of Schrödinger operators and self-adjoint conditions are essential in physics because they arise in many interesting models. The other classical result is that self-adjoint operators also create dynamical evolutions. So we have Stone's theorem, which says that if you have a self-adjoint operator, then that induces a one-parameter group of unitary operators just by using the spectral theorem and plugging the operator into the exponential function. And that group of unitary operators on the Hilbert space exists for all time. On the other hand, we also have classical systems, and we have classical mechanics, and there we all know that the dynamics of the classical system is driven by the Hamiltonian flow. And that Hamiltonian flow, which comes from the configuration, is the solution of a differential equation, and that solution may not exist for all time, so it might not be globally defined. And there should be some correspondence between classical system and quantum systems. And here's a, I call it a folk theorem, which is not always correct, but it seems in a way reasonable, and it says if you have a Schrödinger operator, which is written in the second line here, with some potential, nice potential, let's say, then this is self-adjoint on its natural domain, if and only if the Hamiltonian flow equations, which are formed from the Hamiltonian here, have solutions that exist for all times. And this leads to the notion of the classical completeness, which is completeness in the metric sense, so the solutions exist for all times of the classical system, and quantum completeness, which is basically self-adjointness of this Schrödinger operator. However, this theorem, as it's stated here, is not always correct. And there are counterexamples in either directions of the theorem, so it could not be true in that generality at least. However, I think one can say that there is some truth in this statement, and it's an interesting problem to somewhat discover how much truth is in that statement under additional conditions. So now I want to come to the concrete quantization model, which I'm interested here, and that is what is called the Berzin-Toeplitz quantization. And here we look at the space Cn, which we may see as the cotangent space of Rn with a complex structure. And there we have a family of Gaussian measures, d mu t, and t is just a parameter which at the moment will not play a big role, but we will need it in the end. And you may think of this as a time parameter, and the Gaussian measures are just probability measures, where dV here is the usual Lebesgue measure on Cn. And then with this family of measures, I can produce a family of Hilbert spaces, which I call Fock spaces, or sometimes they're called the Siegel-Barkman spaces, by looking at all holomorphic or entire functions on Cn, which are L2 square integrable with respect to this measure mu t. So for each t we get a Hilbert space. This is denoted by ht2. I call this Fock space because that's intrinsically or naturally isometric to the Fock space in physics. And that space also has a nice property. It's not just a Hilbert space, it's also a reproducing kernel Hilbert space. So that means you have a kernel function, which is this exponential here in the inner product, e to the w z bar divided by t is that parameter, such that taking L2 integral of functions in the Fock space against that kernel produces the point evaluation in Z. So this is this formula which is written here. And then also this Fock space is a closed subspace of the L2 space itself. So we have the orthogonal projection P. It depends in a way also on T, but it's just denoted by P, which projects L2 to H2. And with this projection now we can form a class of Toeplitz operators. So we fix a symbol f from Cn to C. Later on it will be also operator valued, and that symbol could be rather unbounded, and then we produce the operator p times mf. Mf just means a multiplication by f. So we multiply by f and then we project back from the L2 space to the Fock space. And that produces an operator which is called Tf. So passing from that symbol f to the operator Tf can be thought as a quantization. So f in a way plays the role of the Hamiltonian, which is a function on Cn, seen as the cotangent bundle of Rn, and Tf is in general unbounded operator on the Fock space. So the question is, when is such an operator self-adjoint? And to get a feeling what could happen, I want to describe some cases in the lowest dimensional case. We're now just talking about the complex plane. Dimension n is equal to 1, and I want to fix this parameter t to be just 1, for the discussion which follows now. And there's an old result by Janasch, which says that if the symbol of the operator is a polynomial on C, in the variable z and z bar, then I can look at the real part of this polynomial, and that's a real valued function. And in that case, the Toeplitz operator with this symbol becomes a closed symmetric operator. But of course, that's also an unbounded operator because polynomials on C are unbounded. And this operator is self-adjoint if the degree of the polynomial is smaller or equal to. If the degree of the polynomial is higher than 2, then the operator is still closed and symmetric, but it may not be self-adjoint anymore. And to have an example of this, we just look at the degree 3 polynomial, which is very simple. It's just, the Toeplitz is just the real part of z to the power 3. So we may look at the Toeplitz operator with that symbol. That's a symmetric operator, but I claim that that operator is not self-adjoint. And to prove this, we could use one of these characterizations, the classical characterization of self-adjointness. So we may try to find a non-trivial solution of the equation t minus iu equals 0. And if that exists, then the operator cannot be self-adjoint, because self-adjoint means that that only has trivial solution. To find such a solution, we can make some ansatz. So we can take a standard orthonormal basis of the Fock space, which are just monomials to the j with some normalizing constant Cj here. And then we form a series in this, or expansions of possible solutions u with respect to this basis, and then we just test the equation. And since the symbol is an order 3 polynomial, it's reasonable to assume that in this expansion of monomials, only alpha j are non-zero, where j is a multiple of 3. So we assume that alpha 3 plus k, 3k plus 1 and alpha 3k plus 2 are 0. Okay, we may put this ansatz into the equation star, and then what that gives you is an infinite linear systems of equations on the coefficients. So they're written here. It's an easy analysis. And to make things a bit easier to read, you may also write this as a matrix equation. So we can equivalently write the operator equation as the matrix equation 3 star, where it is bold A is an infinite tri-diagonal matrix, which is written here. So it only has entries in the above diagonal and one diagonal below the main diagonal. And at V here should be some vector which is in a L2 Z plus sequence space. And the question is, can we solve that? And such problems have been considered in the literature. So here we have to observe some conditions on that matrix A. And the essential conditions which we need are the one which are written on the last line here. So this infinite sum of the inverses of AK, these entries, is finite because these are they grow of order 3, of order k to the 3. And we have this inequality AK minus 1 times AK plus 1, smaller equal AK squared. And with these conditions, there is a general theorem or result, which is this one. So if we have these conditions, then such a matrix equation with this tri-diagonal matrix bold A has a non-trivial solution V, which is a sequence in L2 space of Z plus. So we can solve this in L2. And that then solves the question. And so this is a source for this statement. And then that shows that we actually have non-trivial kernel of the Toeplitz operator with the symbol real part Z to the 3 minus I. So this cannot be self-adjoint according to the characterization, and we see there is a counterexample once we pass the polynomials of higher degree. So, however, there are also positive results. I already showed you one by Janasch, which tells you that if the degree of the polynomial is at most 2, then the Toeplitz operator with this symbol, the real part of that polynomial, is self-adjoint. And his proof uses also a classical result. I just tell you the idea. So we can, without restriction, first of all, assume that that polynomial takes the value 0 at 0, otherwise we just subtract a constant, which is not essential, of course. And then using the assumption that the degree of p is smaller or equal to, we can show that the infinite series, which is written here, actually converges for all Ej. So Ej runs through the standard orthonormal basis of the Fock space. And this converges if the t is small enough. So if there's some delta such that for t smaller than delta but positive, that will be converging. Yeah, and then we have Nelson's theorem, which tells us that the operator has to be self-adjoint, because these elements Ej then form a set of what is called analytic vectors, and it's a total set. Total means that the linear span of these is dense, which of course is true for an orthonormal basis. So that is an argument which shows self-adjointness. Okay, I want to produce some other positive results which also hold for more general functions than polynomials, but in the way they are not strong enough to recover actually Jana's results, which I just showed you. So then the main part of the talk should generalize these ideas. So one very simple idea is this. The Toeplitz operator is a projection times the multiplication operator. We very well understand multiplication operators, so we may try to compare how far the Toeplitz operator is away from the multiplication operator. Multiplication operator with a real valued symbol phi can be seen as, of course, an operator on the R2 space, and we may write this as a 2x2 matrix of operators if we decompose the R2 space as an orthogonal sum of the Fock space and its orthogonal complement. And then a simple calculation shows that the multiplication operator m phi with the symbol phi and the Toeplitz operator t phi in this matrix representation are just related by the matrix equation which is written here. So if you compare both sides, we know basically everything about the multiplication operator. That's a very simple operator. And we want to know something about the Toeplitz operator with the symbol phi. So what we have to control is the matrix which is written here on the right-hand side, where this operator h phi and h phi star appear. So these are the Hankel operators, which are defined in the first line. So they are projections to the Fock space, multiplication by the symbol, and then projection to the orthogonal complement. And h phi star is of course the adjoint of this. And then the very simple observation is that if this Hankel operator h phi is a bounded operator, then the right-hand side is a bounded perturbed by the multiplication operator, and the multiplication operator is self-adjoint. So in that case also the Toeplitz operator, the whole left-hand side is self-adjoint, so all entries are self-adjoint. In particular, this Toeplitz operator t phi is self-adjoint. So the problem now is to prove under which condition such a Hankel operator could be actually bounded, and that should hopefully also work for unbounded symbols, which then lead up to unbounded operators. This question can be in a way fully answered, and I want to recall the answer to this question. So the question is, for which real valued symbols is the Hankel operator pf m phi 1 minus p a bounded operator, and in particular for which polynomials or real valued polynomials would that be a bounded operator? And to answer this question, we can look at what is called the mean oscillation of a function. So mean oscillation of a function is this. Phi is a function on the complex plane, which is thought as a symbol, and then we assign to this a new function, which I call MOT phi of z. It's a function of z. T is just a parameter which can be fixed. And it's a difference of these two functions here with these twiddles, where the twiddle t means just a heat transform. So we take some kind of average of the function phi by, or f by taking a convolution integral with the heat kernel, this Gaussian kernel here. But that produces a new function. And with this new function, we can define what is called a mean oscillation. The mean oscillation is the supremum of the square root of this function over the complex plane. And that's a semi-norm on functions. And if that is finite for a function, we call the function a bounded mean oscillation. So there's a few observations to make here. This mean oscillation, of course, depends on t. If you change t, the function will change. Also, the semi-norm depends on t, but the space BMO itself does not depend on t, so it doesn't matter which t I choose. Certainly, a BMO of C contains all essentially bounded functions, because essentially bounded functions under the heat transform are essentially neutral. Functions in BMO, they have a slight growth at infinity is allowed, or slight singularity is allowed, not too much. So in particular, BMOC contains linear polynomials. These are examples of unbounded functions, of course. And now the following is true. If you have a complex valued symbol, and then you can simultaneously characterize boundedness of the Hankel operators with that symbol and its complex conjugate. And they are both bounded simultaneously if the symbol is in BMO. So BMO is in a way the largest space which produces bounded Hankel operators. And if you have a symbol in BMO, then this is always a condition on F and F bar simultaneously. So it always gives you simultaneous condition on Hankel operator HF and HF bar, because the mean oscillation is invariant under taking the conjugation. So in our setting, we're interested in real valued function, then we do not distinguish F and F bar, so we have a if and if characterization which says that the Hankel operator HF is bounded if and only if the symbol F is in BMO. And BMOC contains unbounded function. So one may ask what polynomials are in BMOC. So this is a rather simple observation, because for polynomials we can easily calculate the heat transform. And it says that a polynomial is in BMO if and only if it has degree smaller or equal 1. And in that case, precisely HE and HP bar are bounded operators. These two Hankel operators are bounded. So there are not so many interesting polynomials in BMO except for the linear ones. But at least for those, now we get a characterization of self-adjointness, and of course also for non-polynomial symbols in BMO. So this is now the outcome of the discussion. So if we express the multiplication operator as a 2x2 matrix with respect to the orthogonal decomposition of the L2 space, then we see that Hankel operators are bounded if and only if the symbol of the Hankel operator denoted by phi here is in BMO, and in that case the corresponding Toeplitz operator T phi is self-adjoint, and that applies to some slightly unbounded symbols here. However, it does not prove Janna's result for second order polynomials, not even that one, because the polynomial real part of Z square, which he considers, is not in BMO, it's the second order, and in particular the Hankel operator with this symbol is an unbounded operator. However, the Toeplitz operator, as Janna's result based on Nielsen's theorem shows, is still self-adjoint. So for polynomial symbols looking at BMO, this is maybe not a very sharp method. So we can only recover self-adjointness of Toeplitz operators with polynomial. In this joint work here, and to explain the result, I have to introduce the notion of the Bersian transform of an operator on the Fock space. So we have seen that Toeplitz operator TF is a kind of quantization where we assign, we take a symbol f and we assign to this an operator. But since we're working on a reproducing kernel Hilbert space, we have also a way to go the other way. So to take an operator and assign to this a symbol, some kind of inverse quantization. And this is called the Bersin transform. And it works like this. We take an operator A on the Fock space, it could be an unbounded operator, and then we produce from this a symbol by applying it to the normalized reproducing kernel and then taking the inner product with the normalized reproducing kernel. That gives a complex number. And this normalized reproducing kernel in our case is rather simple, it's just this exponential function. And here's how the heat transform comes in. If in particular I consider a tuplets operator, so A being a tuplets operator with a symbol, let's say F, and if that symbol is not too unbounded, which means that F times these normalized kernels, these exponentials, are still in L2. That includes polynomial growth or even linear exponential growth function, so it's some not too hard, not too strong condition. And then we can produce this, do this inverse quantization of the tuplets operator. We do the Bersin transform. The result will not be the symbol of the operator, but the heat transform of the symbol. So this heat transform is some kind of smooth version of the original symbol. And that's how the heat transform enters the analysis here. So now let me just give you the main result, and then in the last minutes I give a few ideas about the proof. And it says the following. So if we have a measurable polynomially bounded function with values in R, and now this parameter t, which appears in this family of measures, comes into play. Now if we assume that we have some parameter s, which is in the interval 0 t half, this t is the t which appears in the Gaussian measure. And if we assume that for such an S, all first derivatives of the heat transform of that symbol at time S have a bounded oscillation. I'll explain what bounded oscillation is. Where phi 0 is just phi. So if S is equal to 0, then it's just the identity. Then from this we can deduce that the tuplets operator with the symbol phi is a self-adjoint on the maximal domain, and we have certain spaces Cj which form a core for the corresponding operators. And here are three possible choices of cores. You can, for example, take all polynomials. You could take the span of these reproducing kernels here, where W runs through Cn, these are all total spaces. Or you may take a Schwarz space, Srn, in L2Rn, and then you put it back with the inverse Barkman transform, which is a Hilbert space isometry between the Fock space and L2Rn. So these are the so-called Schwarz elements in this space of entire functions. All of these form a core. So this gives in a way a nice characterization of essentially of self-adjoint operators, which includes all the previous ones. And now I think I have a few minutes left, and I want to give an example and also an idea of the proof. So in particular, if you have a quadratic real value polynomial, which comes from the result of Janasch, then we can look at all first order derivatives. And if the polynomial is quadratic, then they are linear. If they are linear, we have seen they have bounded oscillation. So in this case, we can apply the theorem with S equals 0, and we produce self-adjointness of a TP. Why is the parameter S actually important? In the theorem, we want to take derivatives. And you may ask whether this property of being self-adjoint has something to do with the regularity of the symbol phi. So the phi is an unbounded, it could be some very rough and non-continuous even function. The regularity in a way does not play a big role, because if you have a very irregular function, this theorem allows you to put it into the heat transform. The heat transform is immediately smoothing and gives you a real analytic function. So you could take, in that case, first order derivatives of values of the heat transform for some S which is bigger than 0. So this is totally well defined. So for polynomials we don't have to do this, and we can work with S equals 0. So this is maybe this remark here. Differentiability of the symbol is not very essential. We can, because if you have a very rough symbol, then you apply the heat transform for some s bigger than 0, then what the result is real analytic and you can take derivatives. So the idea of the proof is this. So we use basically two main ingredients. One of the main tools is the commutator theorem, which is a well-known theorem and shows you essentially self-adjointness or self-adjointness by comparing your operator with another operator which you understand well. So this is the theorem in an abstract fashion. You have a separable complex Hilbert space H, and assume you have an operator which is bigger or equal C times the identity C is positive. And it should be self-adjoint, and you have some core which is denoted by D. And now you want to test whether another operator A is self-adjoint. So if that is symmetric and fulfills these conditions 1 and 2, so in a way it is below the operator n, which you know it's self-adjoint in the sense of this inequality here on the domain. And you have also 2, which tells you that A and n and A are not too far away from each other. And if n then is self-adjoint, then A also is essentially self-adjoint on the domain of n, and any core of n is also a core for a self-adjoint extension of self-adjoint extension A bar. So that is a way to get self-adjointness, or essentially self-adjointness of an operator. So in our case, we have to pick such an operator n, which we understand well in the setting of the Fock space. Of course, there are many choices. There are many operators which are known to be self-adjoint. And I want to prove the theorem first in the one-dimensional case with this parameter s, which appears in the heat transform as 0. So we may take some symbol phi from the complex plane to the reals. And we assume that is differentiable, and the first order derivatives are bounded oscillation. That is our assumption in the result. And then we have to choose a good operator from which we know that it is self-adjoint and it can be used in the commutator theorem. And that operator, so one very intrinsic choice I would say is the operator 1/2 times Toeplitz operator with the symbol quadratic set, so absolute value of set squared. And that can be considered with some domain, for example these ZJs which I defined in the theory. And then we take another operator, A, which is the Toeplitz operator with the symbol phi, which we want to understand. And here, this operator n, in a way, is just a quantum harmonic oscillator. And it fulfills the condition of the theorem that's easy to test. In fact, it's also a product of Toeplitz operator with linear symbols. And now what we have to do is we have to check the conditions of the commutator theorem for this pair of operator n and a. So there's some work one has to do, it's not too complicated, but then we obtain the result in the case s equals 0. So this first step only works or gives you a good criterion in the setting where phi is a differentiable function. We can take derivatives of this. And to generalize the theorem, if you want to go away from the differentiability condition, you can use another ingredient, which is also a classical theorem. And the idea is, if you have a function, a symbol of the operator, which is not smooth or not differentiable, could be very rough, you can try to approximate it with the heat transform for very small types. And then apply the first step to these heat transforms or operators with a symbol as a heat transform and use the first step because these are real analytic functions and you can take derivatives. But that problem somehow, so essential ingredients of this problem is that you have to estimate the norm of a difference of Toeplitz operators. Both have unbounded symbols. So that's again a Toeplitz operator with unbounded symbols. So you have to get a control of the operator norm of a Toeplitz operator with unbounded symbols. And there's an old theorem by Berger and Coburn which actually tells you how to do that. And it says this: if you have a symbol on Cn with values in C, measurable and polynomially bounded, it could be even worse, but that's a good assumption for us. And then t is that parameter in the Fock space construction, which appears in the Gaussian measure. So now if you take a time which is smaller than half this parameter, call it s, then we have a nice estimate. Then we can estimate the operator norm of the Toeplitz operator by the supremum's norm of the heat transform of the symbol or this parameter. So if the symbol has the property that after some time putting it into the heat transform, it becomes a bounded function, and that time should be smaller than t half, then the theorem says that the Toeplitz operator with that symbol is actually bounded. And you have this inequality of the operator norm. So what could happen is this. You could, for example, have a symbol on Cn, which is very unbounded, but let's say it's very strongly oscillating. So now if you consider the heat flow, you consider this as an initial condition in the heat equation and the heat flows, then after some time this oscillation may go away. So it may happen that after some time the symbol becomes bounded and then even may vanish at infinity. So if this happens before t half, then the Toeplitz operator with that symbol is unbounded, is a bounded operator. That's what the theorem says. So we can apply this theorem, and here's a simple proof to estimate the difference between the Toeplitz operator with the symbol phi and the heat transform of phi at some time s. And it says if this s is small enough, so in the interval 0 t half, then we can estimate this operator norm by the supremum's norm of the corresponding heat transforms. And the heat transforms are a relative function, and we can try to estimate this supremum's norm by just using the integral expression, the Gaussian kernel of the heat transform, and put the derivatives under the integral and use the bounded mean oscillation property to actually get a bound on this difference. So if we have a bound on this difference, then that tells us that the Toeplitz operator with this potentially very rough symbol phi and the smoothened out symbol is a bound operator. Difference is just a bounded operator. So we can apply our theorem to the one with the heat transform as a symbol, and then transfer the result to t phi because it just differs from that one by a bounded operator. And that's the second step. So the operator t phi is a bounded perturbation of t twiddle s, if s is small enough. And that one is self-adjoint, and therefore t phi is also a self-adjoint operator. So I think in the last 3 minutes, I just want to tell you a few extensions of this. From the application point of view, it is interesting to have this result not just for Toeplitz operators with complex valued symbols, but rather with symbols again in the space of operators, in the space of Hermitian operators acting on some separable Hilbert space V. This Hilbert space could be, for example, the V-valued Fock space, so entire functions with L2 condition valued in a Hilbert space. And then one can check that this Berger-Koban theorem, which was originally proved for just C-valued symbols, actually extends also to complex, to operator-valued symbols, so that allows you to extend our main result of the self-adjointness. Another case where we can prove these things are what are called Hermitian B of V-valued continuous quadratic forms on the space of Schwarz elements in the V-valued Fock space. I'm not defining this here. Or we could also think about pseudo-differential operators in the Weil quantization. So these are, in a way, generalizations of these Toeplitz operators, which we look at here. And we can also look at certain Schrödinger operators, which act on L2Rn and transport them via the Barkman transform to the Fock space. And then, in some cases, or some potentials, these produce the Toeplitz operators with unbounded symbols, and then we could apply our results to these type of operators. Okay, so here's a concrete example, which I will skip due to time reasons, but I want to finish with a question I have started with. So now we have a quantization scheme where we go from a symbol to an operator, and we have a parameter t, which is this parameter in this family of Gaussian measures. So you may think of this as a semi-classical parameter, which we have which tends to zero also in our proofs. And then the question is, now if we have this family, T-dependent family of tuplets operators, how does self-adjointness behave in this parameter? So in particular, what happens if this parameter goes to zero? So there's a typo here, T goes to zero. And the conjecture is this. So for reasonable symbols of the operator, here the following are equivalent. So this F is classically complete, maybe up to a null set of initial values, in the sense that if you consider the corresponding Hamilton equation, then the solutions exist globally in time, should be, in this quantization scheme, equivalent to the fact that these tuplet operators, TF, are essentially self-adjoint, at least if you take very small quantization parameter T. And that is what I called, or what one calls, a quantum completeness. So that's an open theorem, but I assume that under the good conditions, you can get a positive answer to this one, and not just study the self-adjointness of the tuplet operator TF itself, but also how it behaves in such a parameter space of semi-classical parameter, for small parameters in particular. Yeah, I think so my time is up. Here are a few references. The first paper contains basically the theorem, which I have shown you, and then there are some more classical results by Janasch, and also the relation to the Berger-Coburn theorem, where we give a short proof of this. This was an essential ingredient of the proof of the main result. And yeah, let me finish with a picture of our nice university. Thank you for your attention.
Yeah, I can hear. Thank you very.
I also hope so, to be back there and see you there. So I wish you a successful conference, and yeah, many good, interesting talks. Thank you for the invitation.
Thank you.
To introduce Dr. Sumesh K, the assistant professor from the Department of Mathematics at IIT Madras. He works on a variety of topics associated to operator algebras. He did his PhD from the Indian Statistical Institute under the guidance of Professor Rajaram Bhatt. And after that, he was a postdoctoral fellow at Math Science. Okay. And he will be talking about Gaussian channel today. So.
Yeah, thank you, Sunjan. And first of all, I'd like to thank the organizers, especially Narayan, for the kind invitation and nice hospitality. So in this talk, I'm going to give a brief introduction to the theory of Gaussian states and Gaussian channels, and which appears in quantum information theory and quantum optics. And this talk is based on a joint work with Ravana Devendra, and Kichu Charyanjo. Okay, so to begin with, I want to say a few words on the quantum information theory. So in quantum information theory, what we have is that we have information which we encoded in the states of a physical system. Okay. Then this physical system has a mathematical description, namely this state of a physical system, which we call as quantum system or quantum state. So this we can give a mathematical description, namely they can be mathematically described as trace class operators, which are positive trace class with a trace equal to 1. Okay, now what you want to have, that you have a quantum information, either you want to transmit from one place to another one, or you want to do operation on this quantum information, or you also want to see how the quantum information evaluation happens over the time. So that means you have to transmit the quantum information from one place to another one through a quantum channel, quantum communication channel. or you want to do operation called quantum operations, or you also have to describe the evaluation. So you have quantum channels, or you want to do quantum operations. Again, these things also can be given mathematical description, and these are mathematically described using a special class of positive maps, namely completely positive maps, which are trace preserved. Okay, now if you want to make this content information theory make possible, then what you want to have? You have a physical description here, you have mathematical description here. So if you want to make it physically possible, you should be able to construct these quantum states or quantum channels in a physical lab. No, so can you construct quantum states or quantum channels in a physical lab? So here comes the special kind of quantum states, namely the Gaussian states. So there are special class of quantum states which are readily available in a physical lab. That means you can construct in a physical lab, and which are theoretically more robust. And there are lots of examples. So most of them comes from the quantum optics or quantum information theory. I am not an expert to explain each of the terminology, but at least remember the names. There is something called coherent state, which is something associated with a laser beam. And there is something called thermal states, which appears in the quantum optical theory. And there is something called skew state. Okay, so there are physically, it is possible to make quantum states in a physical lab. Some of them can be very difficult, but still is possible. Okay, now you have quantum states. Now what you want to do? You want to just do operations, or you want to transmit information. That means you want to construct quantum channels. So how you construct quantum channels physically, whether you can do or not. So here comes the special class of quantum channels, namely the Gaussian channels. Again, whether you can construct them or not. And again, it's you can see that there are examples where these Gaussian channels are used. You can construct Gaussian channels physically. So some of them are there's something called additive white Gaussian nodes. Again, this is a very famous channel. I don't know exactly what exactly it is. And there is something called in quantum optical channel. There are some notions which are also special class of Gaussian channels. And there is something called thermal noise channel. All are examples of Gaussian channels. Okay. Now what you have on one side, you have the physical notions, other you have the mathematical description. And what we said is that quantum states, we are given a complete characterization in terms of mathematical explanation, and the quantum channels also you have a mathematical explanation. Now what you want to just see that, what about Gaussian states? That means among these mathematical objects, what are all Gaussian states? Can you give a characterization? And among all the quantum channels, that means among all these special class of mathematical objects, can you characterize what are Gaussian channels? Okay, so in this talk, what I am going to do. Okay, so to begin with, I need a few terminology, some few definitions which are highly technical, but I try to avoid all the technicalities as much as possible. So whatever definition or theorems I am going to state, it may not be the exact definition. This is something called an equivalent characterization of them for the easiness of the presentation. They are okay. So here comes the first definition. So you start with a vector in D-dimensional complex space CD. Then you can define the n-fold tensor product of V, which is inside the n-fold tensor product of CD. Then given any vector V, you can associate or you can construct a vector, which is called exponential vector, which is defined as this way, which is belongs to the infinite direct sum of n-fold tensor product of CDL. Okay. Now one can prove that these exponential vectors, the set of all exponential vectors are linearly independent. And then you can look at the span of the set within this Hilbert space. Then you look at the closure. That closure I call it as the symmetric box space. Okay. Now those who are not familiar with what the infinite direct sum or tensor product, you can simply see, take it in this way. You start with CD. You can construct a new Hilbert space. Forget about what exactly it is. You can construct a Hilbert space, namely the symmetric box space, which will be denoted by gamma of CD. And inside the gamma of CD, you have a special class of vectors, namely exponential vectors, and which has a property that they are, in some sense, they are dense. Not exactly dense, they are quarter. So now if you want to define any operator on this Hilbert space, it's enough to define operators only on the exponential vector. Okay. Now on this Fock space, this special class of Hilbert space, introduce a special class of all operators, unitary operators. So how you do that? You start with a vector u in CD, then given any u, I can associate a unitary operator from this Fock space to Fock space. How it is defined? So as I said, I don't know how to define on the entire vectors here. It's enough to define only on the exponential vector. So on the exponential vectors, how these operators act is this way. Okay. Now what you can see that this is actually from a unitary operator. So given any vector u, you have a unitary operator on the Fock space. This unitary operator, this Weyl operator, and this Fock space has lots of properties. Two properties which we may use it. Is something called a factorization property. What is that? See, whenever you are given two numbers, d1 and d2, with the property that d1 plus d2 is d, then CD you can realize as CD1 direct of CD2. Okay. Then if I look at the Fock space on CD, that means Fock space on CD1 direct of CD2. What you can just see that they are as Hilbert space, they are isomorphic to the Fock space on CD1 and the Fock space on CD2. And again, the isomorphism is given this way. And with respect to this decomposition, the Weyl operator decomposed as this way. Okay, so this is the something called the factorization property of the Fock space and the Weyl unitary operator. Okay. Now here we are mainly dealing with only the D-dimensional Hilbert space CD. So this is you can think of this as a real vector space, but we try to relate as a Hilbert space. It's a 2D dimensional with inner product given by the real part of the inner product. Okay, then you can sometimes we will realize this CD with R2D in a canonical way. And if I look at the scalar particular minus I times the identity matrix, under this isomorphism, it will be identified with this special matrix J2D. Okay. Now I want to define something called a symbiotic transform on CD. So you start with a real linear map. So now here everywhere I am realizing it as a real Hilbert space. Okay. So you start with a real linear map L on CD. I'll say this is a symbiotic transformation if it preserves the imaginary part of the inner product. Okay, that means this condition. And one can see if I realize CD with as R2D, then this inner product property we can interpret as an equivalent way of matrix equation, namely L transpose J2D, L is equal to J2D. Okay, so now there's the symbiotic transformation at the level of complex linear map, it maps to satisfy this property. At the level of matrices in R2D, this satisfies this condition. So we denote the set of all L satisfying this property by this set SP2D, J2D. So they are called the symbiotic matrices. Now again, why the symbiotic matrices? Now what you can just see that given any symbiotic matrix, you can again you can associate a new unitary matrix on the Fock space, which we call as a Bergoglio of unitary, which satisfies this condition gamma L WL gamma L star is equal to W of LUL. And this is not in general unique, it's unique up to a scalar of modulus 1, but additional extra condition, then we can just see that it's a unique unitary operator. So what we have done, we have the Fock space, then given any vector you have a Weyl operator, and given any symbiotic matrix, you have another unitary, namely Bergoglio gamma L. So these two operators we will be using later. Okay, now I just actually said that quantum states, they are represented as positive trace class operators of trace 1. So let me give some notation. So this represents the bounded operators on the Fock space, and B1 represents the trace class operators. Now my states, quantum states are basically positive trace class operators with trace 1. Okay, now among these states I have to classify what are all Gaussian states, correct? So to do that I need the notion of quantum characteristic function of a state. So what is that? You start with a state, then associated to that state we can define a map which I denoted by rho hat, which is a map from CD to C. How it is defined? It's defined as the trace of rho WZ. Okay, so this map is known as the quantum characteristic function. These are, you can ask why this characteristic function. There are some resemblance with the Fourier transform of measure or expectation. I don't want to go into the details. So this is what you have. Now we use this quantum characteristic function to classify quantum states. So amongst quantum states, what are all Gaussian states? So here comes the definition. So So the definition is the following. You start with a state, then I will say that this is a Gaussian state if the quantum campus function has a special form. That means you should be able to get a vector f from the CD and another real linear operator s on CD such that this quantum Fourier campus function is given by this way, exponential minus a real part mz minus real part of z sz. Okay, so there are some different definitions with some different scaling and different interpretation, but all of them are equivalent, but the scaling will reflect only in the computation. Okay, but this for the time being I will take this as the definition. Okay. What I said is that you start with a quantum state. I say that it's a Gaussian state if I have two parameters. One is m, another one is s. Okay, so given any row, I have a pair ms. In fact, you can see that whenever that exists, they are unique. And conversely, whenever I have a m and s, but this s, or if you start with any real linear operator s, that not always may not be covariance matrix. Okay, so I forgot to mention that this m is known as the mean vector and s is known as the covariance matrix. So given any linear operator that always will not be a covariance matrix, it needs an extra condition, namely s plus ij. This is a j2d. This must be a positive semi-definite matrix. Okay. There is one-to-one correspondence. So you have a row, you have a parameter m and s. Conversely, if you have m and s, where s satisfies this condition, that will give me a quantum Gaussian state. So quantum Gaussian states are completely characterized by these two parameters m and s. Okay. Now let me give some example. So just remember the first real life example which I gave, namely the coherent states, thermal states, and skew state. Okay. So what are coherent states mathematically? They are states given by this way. There is some scaling, and this is a rank 1 operator EU. So let me explain what is the notation. So this in general, if I start with any two vectors x and y from a Hilbert space, this Dirac notation. So this is a map from H to H. How it is defined? Any z goes to inner product y with z x. Okay. So in particular x is y, you can see there is a self-adjoint operator, and if x equal to y and both are unit vectors, they form a trace state. Okay. So if they are not unit vectors, let me just make it scale so that you will get a state. Okay. So this is not coherent state mathematically. Now what are thermal states? Thermal states are Gaussian state with the mean 0 and covariance matrix S, which is of the form 1 by 2 part S T by 2 half part S T by 2. Well, this T has a special name called I think thermal constant or something, I don't remember exactly. Inverse temperature, not thermal, immense temperature. It has a physical meaning. Again, I am not an expert in those. And skew states are Gaussian states of special property, namely rho S L transpose S, where L is of a special class of similarity matrix given by A0, 0, 1 by A. Okay, so this is an example of quantum states. Now you may, Gaussian state. Now you may ask, if I have Gaussian state, whether you can construct new Gaussian state out of it. So there are ways of doing that. That if I start with the two Gaussian states, if I take the tensor product, that will be again a Gaussian state. And if I start with the Gaussian state, and if I conjugate with the Weyl unitary and the Mogollioff unitary, that will again give me a Gaussian state. And another way is that if I take any Gaussian state, there is something called a partial trace, just take it granted, some operation, then that also will give me a new Gaussian state. Okay, so there are ways of constructing Gaussian state out of new old Gaussian state. Okay, now so look at here. So here I said that WU, this is a unitary, gamma L is a unitary. So if I represent the entire thing, W of U, gamma L by V or capital U, then this is what U rho ms U star. Correct? So I have a Gaussian state, I am just conjugating U rho U star. So you may ask whether if I start with any unitary U, whether it is the case that U rho ms rho is also a Gaussian state or not. So in general that is not true, but only in special cases when U is a Gaussian unitary, they form a Gaussian state again. So what do you mean by Gaussian unitary? Gaussian unitary is a unitary of the form which are scalar multiple of W of U gamma L. That means some scaling will come here. So these are the only possible unitary which when you take conjugation will be a Gaussian state. Okay. So these are all about the Gaussian state. Now you want to come back to what is Gaussian channels. So before that, I just simply recall what quantum channel. So we have given complete description about what are Gaussian state. Now what I am to do, I am just telling you what is quantum channels and Gaussian quantum channels. So I already said that quantum channels are a special class of map, namely trace preserving completely positive maps. In the previous talk, when Tathagata he gave a abstract definition of the completely positive map. But I don't want to go to that definition, but I just give an equivalent definition which is coming from the standstill representation. For the time, because this is the only representation which I need. So I'll say, if I start with a linear map, bounded linear map, from the trace class operator, so bounded is with respect to the trace now. So if I start with a bounded linear map psi, I'll say this is a quantum channel. So first of all, I need this has to be trace preserving. So I have the trace preserving property, then the next property is the CPness. Okay, so that I'll put in a different way, that completely positive map I characterize by this way. So what does that mean? I need to, there should be a Hilbert space H, and there should be a state rho on B, this Hilbert space K, and the unitary operator U, this tensor product, so that psi of T will be given by this way. Okay, so here trace 2 is again partial trace with respect to the second component. So if I, this bounded linear map psi is given by this form, then I will say this is a quantum channel. Okay. Now what I am to do? I want to characterize among these quantum channels what are all Gaussian quantum channels. That means what are all channels which maps Gaussian state to Gaussian state. Okay. So this is the sense which we have to ask. Now before asking that, we have to just see whether such examples exist. First of all, can you give some examples of quantum channels which have this property which maps Gaussian state to Gaussian state? So here comes the example, which is written in terms of the proportion. So you start with two numbers d1 and d2, and the sum is d. Then this CD we are writing as CD1 direct sum CD2, but CD1 we are writing as R2D1, CD2 we are writing as R2D. So you write as U1 plus U direct sum U2. Start with a symbiotic matrix L. Then we can see that if L is a symbiotic, L inverse is also symbiotic. So then this with respect to D, with respect to this decomposition, I can L inverse, I can write a 2x2 block matrix. So you look at represent L inverse as this way, L11, L12, L21, L22. Then if I define psi from this trace class operators on block space to in this following way, you look at T, any T from the trace class goes to trace to W gamma A, T tensor gamma 0 identity W gamma A. Okay, so this map will give me a quantum channel in the sense that it maps, it's not only quantum channel, it maps Gaussian state to Gaussian state. So there are examples of quantum channels which maps Gaussian state to Gaussian state. So remember that if I look at here, this is a special class of unitary. So as I said, I want to classify, among these I want to classify what are all Gaussian channels. So that means here what are the parameters? I have the Hilbert space here, I have the U here. These are the only things. So how I can parameter. So this unitary, whether every unitary will give or not. So previous example we saw that conjugation, unitary conjugation of Gaussian state need not be Gaussian state always, but only for special class, namely the Gaussian unitary. So that is what this Gaussian unitary comes into. So capital U must be of this form, and then if I this state, if I am not taking arbitrary state, but I will start with a particular Gaussian state. Then this channel will give me a Gaussian channel which maps Gaussian state to Gaussian state. Okay, so this is most of the time in physics is taken as the definition of the Gaussian channel. Okay, by Gaussian channel, whenever they mention mean that a channel which has this particular form. So this was a question very from decades whether these are all only Gaussian channels or not. That means whether these are the only quantum channels which maps Gaussian state to Gaussian state. Actually, this problem it was there in the literature for a long time, but we heard about this problem first time from KRP when he gave a series of lectures in ISI Bangalore a few years back. But that time we did not work on that, but recently only we started working on this problem. So what we want to just see that whether these are the only Gaussian quantum channels or not. Okay, so that means this is the question, or these are the only Gaussian channels. So what we proved is that yes, these are the only one. Okay, so previous mathematician take definition of a Gaussian channel as the following way. It's a quantum channel which maps Gaussian state. This is natural way to define the Gaussian channel, correct? But physicists taken this as the definition. But it was taken more or less by everyone or assumed that this is the only thing. But so far there were no mathematically rigorous proof to prove that this claim is right, because these are the only one. So we try to get a proof for that. We finally succeeded in proving that. We proved that these are the only quantum Gaussian channels. Okay, so this was the one definition, and this is another definition that was existing in the literature. We proved that both are the same. But there are even more definitions in the literature. So let me just quickly go through them. Okay, so what we have to have? We have to have a quantum channel. Then we have a rho, which is a Gaussian state, which is given by parameters m and s. Then we have to have a quantum channel, means you have to get a channel which maps this. Again, the output is again a Gaussian channel. That means this also should have a mean vector and a covariance matrix. That means this rho output is completely depending upon this one. That means this will be completely depending upon this m and s. So the mean of this vector will be depending upon this m and s. So the mean of this output will be some function of m and s. Similarly, the covariance matrix also must be a function of m and s. Correct? Alpha to m and s. Now there is a paper by Polity when he was trying to study quantum dynamical semigroup of Gaussian channels. He introduced the notion of Gaussian map. So what we call it as a Gaussian map. So the definition was the following. Gaussian map is a positive map on the Fock space with the property that, so this is my psi. Psi is said to be a Gaussian map if there exists functions alpha 1 and alpha 2. It's not that alpha there exists function. He also assumed that these functions are continuous. Okay, so there exists continuous function alpha 1 and alpha 2 such that the psi maps any rho ms to this way. Okay, that means the transformation of the mean vectors is continuous and the transformation of the covariant vectors is also in a continuous way in terms of the m and s. Okay, then what he proved is that if this happened, whenever there exists alpha 1 and alpha 2 exists, then he proved that alpha 1 must be, so there exists x and y which are matrices, and another vector w from the R2D or CD, such that this alpha 1 ms, the first component will be x transpose m plus w, and alpha 2 ms, this is x transpose s x plus y. So this is what we proved. The assumption that alpha 1 and alpha 2. But what we observed is that, so here if you want to have this property, it tells you that this is my covariance matrix. Okay. So if I simply start with x and y, it's not necessary that given any covariance matrix S, this x transpose Sx plus y will give covariance matrix. Okay. So that was what superposed some gap in his proof. So what he needed, given any x and y, this may not be a covariance matrix always. So you need some additional condition on x and y. Namely, there is some condition, I just mentioned that. But when you assume that one, that will necessarily follow that this sign must be a completely positive map. Okay, so it's not that if you start with a positive map, you may not get x and y which satisfies this condition, with this property. Okay, so first thing, and secondly, what we observe is that in the definition he assumed that they must be continuous map. But we prove that this continuity is superposed. You don't need us to assume this one. Once you assume this property, alpha 1 and alpha 2 will be necessarily a continuous map. And once you have that one, just positively will not give me this conclusion. But if I assume that psi is a completely positive map, then we will come up with this one. Okay, so that is the third equivalent definition. We proved that this is again equivalent to this one. Namely, so there exists x and y and w such that this quantum channel, if it is a Gaussian channel, or if it maps Gaussian state to Gaussian state, then any rho ms must go to this one. So this is my alpha 1 and this is my alpha 2. Okay. Now again, once you have this psi, now psi is a mapping from the trace class to trace class. You know that if I take the dual of this trace class, I get the complete bounded operators. And on the completely bounded operators, what we know that the very unit operator which I define, they actually form a weakly dense with respect to the WOT topology. So that means they form a dense subset with the appropriate topology. So that if I define this size star, look at the banal level of this map from the boundary operators, then that map will be of this form. So it was another definition which was available in the literature, which actually forms from here also. So one definition was this one, which is they take it as the definition of Gaussian channel. Another definition was this one. Okay, but these two are, you can easily say they are same, but whether these are equal to saying that it maps Gaussians to Gaussian state, it was not clear. But we prove that all these are equivalent conditions. Okay, and again, if you are familiar with completely positive maps, which tells you that if I have a completely positive map, any ambulation is also a completely positive map. So you may ask whether, what about the ambulation? Whether that also take Gaussian state to Gaussian state or not. So we observe that even that is also okay. It's not just that the map Gaussian to Gaussian, any ambulation will also maps Gaussian state to Gaussian state. So these are the complete characterization of Gaussian channels. Any of the definition, if you take, everything is equal. Okay. So the proof was some of them were some computation, but some of them were slightly technical. For example, 1 to 2. 1 to 2 we already observed. But if I have to go to 2 to 3, again from here we observe. Now if I have to go from 3 to 1, what I have is that I have x and y, and from that I have to get a Gaussian unitary. But Gaussian unitaries are coming from W of u gamma l. I have to get a u and I have to get a l. How I get that here? So out of this x, y, and w. So that was the crucial step in proving this theorem. So which we actually achieved by proving this proportion. Okay. So what we are given is that we are given two matrices x and y, and then out of this x and y, you have a symplectic matrix. So what we try to do is that we try to get a symplectic matrix with x as the first component, and also we assume that the x and y. So if I look at here, I say that if I start with an arbitrary x and y, it may not give a channel. Then necessarily this condition must hold. Y plus I j minus x transpose j dx must be positive, and that will necessarily tell me that y also must be positive. So this condition is already there. Now if I have these two conditions, whether I have x and y, with this assumption whether I can get a symplectic matrix or not. So that was the crucial step in proving previous theorem. And you obtain that, yes, if I start with an x and y, I can always get a symplectic matrix with x as the first component. And not only that, if I look at the second 1, 2 and 2, 1 component, it has the property that L21 transpose L21 will be the matrix Y which we started with, and with some for some data. Okay, so this again, it was very technical proving this one. We have to use so many technical lemmas and some algebraic computation. And also we need to use something called Gram-Schmidt orthogonalization process. So sorry, symplectic Gram-Schmidt process to get this one. Okay, so this is what all about the quantum Gaussian channels. Now we have a complete characterization of the Gaussian quantum channels. Okay, now you may ask this way. So if I start with x and y, I know that I can get whether you can get a channel. So whether you start with x and y such that x and y has the property that given any covariance matrix S, x transpose Sx plus y is always a covariance matrix. So you may ask whether if I start with x and y, whether I can always get a Gaussian channel which has the property that any Gaussian state with the mean m and s will go to a Gaussian state with a covariance matrix x transpose Sx plus y. Okay, so this was one of the questions which KRP asked in one of his articles, whether you can always get such a Gaussian channel or not. What we proved that this is not always possible. This is possible only if x and y satisfy this condition. Okay. So now I have to just say a few more about KRP. So look at this one. So here what we did there, I start with x and y. Then the question was whether I can always get a symplectic matrix with x as the first component and 2, 1 and 1, 2 component has this property. So this was again one of the property, one of the question which KRP asked in one of his articles. Got a symplectic dilation. That means you start with x and y, you are dilating into a symplectic matrix. That means you are dilating the x as coming as the first component. Okay. So one of the questions that KRP is one of the 250 or 10 papers probably. So this is a question. what are the necessary and sufficient conditions for the existence of a symbiotic dilation? If I start with X and Y with the property that, if I start with X and Y, whether you can always get a symbiotic dilation with the property, the first component is X and second component is the property which is a positive matrix here. So what we obtained is that is possible only if this condition is satisfied. And the second question which he asked is the following, given any X and Y, you can always get a Gaussian channel which map this Gaussian state to any Gaussian state with this property. Again, that was one of the corollary which I mentioned just now. We proved that is also possible only under some sufficient necessary conditions. Okay, there was one more problem which he asked in his paper. It was the following. So now we have lots of Gaussian state. Now you may so if I take the Gaussian state, if I take two Gaussian channels now, if I take the composition, what will happen? If I take the composition, Gaussian channel means it maps Gaussian state to Gaussian state. So the first one map Gaussian state to Gaussian state. If I compose it again, that will map Gaussian state to Gaussian. So composition forms preserve the Gaussianity. Okay. So now you can look at the Gaussian state. You can take the semi-group with this operator composition. You may ask, what about this group? What are the, can you get us some smaller class of Gaussian channels which generate entire Gaussian channels? Okay. So for this purpose, he defined a class of channels. So the first one is called the reversible Gaussian channel. And again, so here this reversible channel means a channel which is of this form. So you may wonder that our general form, there was a trace to coming and then there was a product, tensor product was coming there. But again, you can just see that this one again you can represent in that general form. And so these channels of this form are called reversible channels. And there is another channel called bosonic channel, which has the property that channels which maps rho m, any Gaussian state with the mean S, M and S, to a Gaussian channel with mean M and covariance matrix S plus 1. So such channels are called Gaussian channel. And there is another class of channels which we define, namely symbiotic channels, which are of this form. Okay, so here from the general form, what is missing here? There was a WU missing here, but here the trace was missing here. Again, this also you can put in the previous form. And there finally there is something called Gaussian free channel, but this one was defined in terms of the dual map, which is given by this way. So you have a class of Gaussian channel. What we have asked was look at all these Gaussian channels. You can take the composition. So now whether you can get a Gaussian channel which does not come from the semi-group generated by these channels. Okay, but if I look at everywhere, this composition with the Weyl-Unitary, or it is of this form, or it's something like trace part, and or it is of this form. But what we observe, the theorem which tells you that if you look at any Gaussian channel, it is of that form, correct? Either this form, or it will be of this form, or it will be of this form. So that means any channel will be of that form. That means if you look at all this subclass of Gaussian channel, if you take the composition to generate a Gaussian channel. So there is no Gaussian channel which is outside the semi-group generated by this form. So that again completely answers our question, all the questions asked by the KRP. Now finally, we have defined the Gaussian channel. We have said that these are physically can be made in a lab. Now we have the class characterization of Gaussian channel. You may ask whether you can construct Gaussian channels in a physical lab or not. But again, there are difficulties, you cannot make everything. But there are some special class of Gaussian channels which you can construct in a physical lab, which are called linear optical channels. Okay, what are linear optical channels? So linear optical channels are channels of the special form, this one. So it is of trace to gamma L, E tensor, rho zero identity, gamma S. So here W, U was missing there. And L has a, so previous way it was, when I say Gaussian unitary, L was only symbiotic matrix. Okay, but here L is not just symbiotic, it is something called a orthosymbiotic. That means it's symbiotic plus orthogonal matrix. Okay, so any channel which is of this form where L is an orthosymbiotic matrix, which is known as a linear optical channel. So it is experimentally observed that these channels can be physically implemented. Okay, now we already have a characterization of Gaussian channel which are parameterized by three vectors X, Y and W. Okay, now may I ask what about Gaussian channels which are physically implementable? Whether among these parameters can you classify all Gaussian channels which can be physically implemented in terms of the parameters X, Y and W? Okay, so again we succeeded in proving that. We proved that yes, you can completely characterize, but not all. There are some special assumptions you have to make. Look at the channels which can be implemented using multi-port input, that means linear optical channels with D number of environments. So here, whatever D I mentioned, this is something called the number of N1 parameters. So what we prove that any channels, if it has any Gaussian channel which can be physically implemented, if and only the parameters x, y must satisfy this condition. X transpose x plus y must be a identity. That means in particular y is a positive matrix, that has to be a contraction, and from here x also must be a contraction satisfying this property. Not only that, this x transpose q y square root y must be symmetric for some orthogonal matrix q. Again, this condition we can rewrite in terms of a symmetric matrix, but I just leave it right now. So this is what. So when x and y satisfy this condition, then only the Gaussian channel can be implemented using a linear optical channel. So this completely characterizes all the physical quantum channels can be physically implemented. Okay, so this is all what I want to just say, and so this is based on the work with Revan and Kingu. It's recently appeared on the philosophy of transition of Royal Society. Last week it appeared online. This was the paper which I mentioned, K.M. Pasayadi, where he introduced the Gaussian space, but there he defined everything in terms of slightly different. The Hilbert space L2Rn, but L2Rn and Fock space are usually equivalent. So you can have a different interpretation there. And this is the paper where he mentioned all his questions, which we answer right now. And this is the paper which we use to prove our main theorem on the quality. With that, I stop. Okay, thank you for your attention.
Any more questions?
Yeah, so this is something what we are working now. So in field mode, we have to be careful about some more additional conditions. Even the covariance matrix, there is Hilbert-Smith and trace class conditions are coming there. So to handle that, we need the theory of symbiotic spectral theory. That's what Kiran and his friends are doing. That's what we are working on now. Well, so to develop this one, probably we may need a symbiotic spectral theory. So first we may have to develop that to handle this in the field mode. And another question again. This is a finite mode, only CD only we are just working. Now infinite mode means you have started instead of CD you start with Hilbert space. Now even in the finite mode, what about the semi group of Gaussian channels? Again, these are well studied by Italian group of mathematical people, for namely Pangola and his research group. They have said a semi group of finite mode Gaussian channels. They have given a characterization of such semi group in terms of some parameters. We will have to see what about this characterization, whether you think this f of this new characterization, whether you can get a new characterization of the quantum semi-group in terms of the generator and some other parameters also. And further, infinite mode you have to just see it. And also there is also notion of entanglement. Again, that's also important in the confirmation theory. Among these Gaussian channels, what are all entangled breaking Gaussian channels? This is also something which we are working on.
Any other questions? If not, let us thank the speaker again.
Thank you, sir. I would like the chair to give our speaker a token of appreciation. So thank you everyone. This concludes the main talks of the day. Next we will have the contributory sessions which will be at two venues. Venue 1 will be this hall and venue 2 will be on the first floor. The chair for venue 1 is Professor Arun Kumar and the chair for venue 2 is Professor Shankar P. After the contributory session,